In this series, I'm going to take a look at Solidity Patterns. Now, why is it a good idea? Well, it is because it makes the code more robust and reliable, and especially working with blockchain technology, you want your contracts to be reliable. I'll be taking a reference of this wonderful article written by Provable down here. You can check out this article yourself, and I'll be going through and looking into each section as we go along, explaining the pattern that we deal with, as well as implementing a code example. My name's Daniel, aka HashLips, and welcome to the channel where I teach you about code. Now, if you get stuck at any point, like always, go to our channels. There's a Discord or a Telegram channel where you can ask questions, and there's always devs ready to assist. Let's jump into this series. I always say when it comes to code and you want to learn it the best way, it is by practice. So if you want to follow along with these code examples that I'm going to type out regarding the Solidity patterns, then follow along by going to remix.ethereum.org, pause the video, write along with me, and I promise you, you'll become a much better developer. So if you don't know what Remix is, it's basically an online Solidity compiler. It takes the human readable code that we write and turns it into bytecode, which can then be deployed on the blockchain. That's why it's very convenient for us to just open this up on the browser and then code along or code concepts and test it out. It also is a great tool to test smart contracts on a virtual blockchain, which I'll show you in this series. Let's go ahead and look at our first Solidity pattern. I do want to mention before we start that these Solidity patterns were coded in Solidity version 0.4.2. We are going to do our examples in Solidity 0.8.0 to keep to the most current up-to-date Solidity version. It doesn't take away from the fact that this is still important because it's the concept that matters. Behavioral patterns, security patterns still exist in these forms like guard checks, state machines, oracles, randomness, and so on. It's just how we implement it using the code might be a bit different. So sticking with this tutorial, you'll see the most up-to-date code and the certain nuances that changes with the new Solidity version. Let's take a look at the first pattern on our list, which is the guard check. Now, guard checks fall underneath the behavioral patterns group for a good reason. These checks are there to ensure that the user's input into functions or the function execution executes as expected. Without these checks, smart contracts can act in unpredictable ways, and with the immutability of the blockchain added on top of that, it can cause a disaster. I'm going to take a look at a coding example and write one out with you guys, but if you don't understand Solidity basics yet, you can go to my YouTube courses and have a look at the Learn Solidity Basics course over here. We talk about Remix in this course and you'll get a good understanding before you go into the best practices. Let's now jump to Remix and create a new workspace by clicking on this plus icon. Then I'm going to call my new workspace Solidity Patterns, like so, and hit enter. Now we're not going to use all of the smart contracts over here, but I do want to just copy something from them. So I'm just going to simply right click on contracts, then say new file, and this one I'm going to call guard check, like so. So the guard check.sol. Next, I'm going to go into the ballot and just copy everything from here, from the Solidity pragma line and the license. Going to go to the guard check and paste it in there. The reason for this is I hate typing this out, first of all, and we need to specify the pragma line of which Solidity version we are going to be using. Now, like I said, I want it to be everything from 0.8, so I'm just basically going to change everything upwards of 0.8.0 to 0.9.0, which is fine. It's the most relevant one. And then we can get going. We can get started. We can now go ahead and delete the ballot, owner, and storage.sol files over here. So just select them and delete all of them. We don't need them. And I'm also going to delete this artifacts folder that gets generated. So let's look at our fictional example that I want to put to you in order for me to explain guard checks. So when I teach, I would like to make it fun. Let's go ahead and put in place this story. So we have a burger joint and we want to set up a small smart contract that we can use to have people buy burgers, and then let's say we need a refund function in there for if someone disliked the burger. Then we need to refund that person's money. Now, just keep in mind, any of the examples I show you is not production ready at all. These are just simple concepts, but we need these concepts to understand why we need certain patterns and how these patterns will help us make our smart contract more secure. So let's start off by defining the contract. You do that by typing in contract, the keyword, and then the contract's name. Now I said we're going to have a burger joint, so let's say maybe burger shop. Keep it agnostic. So the burger shop contract needs to look like this, and it is going to not inherit from anything. A good practice is actually to call your smart contract the same as your file. So I am going to go ahead and do that, seeing that this is the best practices course. So I'm going to turn the guard check into the burger shop. We'll most probably reuse the burger shop example to explain other patterns as well. So let's just go ahead and do that. Our burger shop is going to need some variables. So what we need to do is let's give it a variable. We're going to give it a UN256 data type. And we're going to say this is the cost. We need a cost of a burger. Now let's just imagine for our example, we only have one burger, one ultimate cool burger that people are going to buy. And this is the only burger that we sell. So we just need one cost. Now we can type out and say that we want our burger to be 0.2 ether. Let's do it 0.2 ether. It's a very expensive burger. And you can go to this converter, ETH converter. So you can type out 0.2, and this is the weigh amount. Whenever you work with amounts in Solidity, it's going to be weigh, the smallest unit of ethereum, okay, of ether, basically. Now, you don't have to do it like this, but this is a way that you can do it, or you can use the keywords. So I can go ahead and say 0.2, and then put in the keyword ether. This will mean that Solidity picks this up and converts this for us into the weigh amount. And it's a way better mechanism to use this instead of all those trailing zeros. The next thing we'll need is a function. Let's create one, and let's call this function buyBurger. The reason for that is we need some kind of way for someone to buy the burger. We need to make this function payable, and let's also make it public, like so. This buyBurger function is going to be public, and anyone can send an amount of ether into the contract and buy themselves one of our burgers. Now, we don't have any way of tracking this at all, who bought a burger or what the case might be, but that's not why we're doing this example. So we're just going to have this function buyBurger, and then also we're going to have a refund function. So let's create a function and call it refund. This is going to be public, and that is it. Let's create another function, and this function would be there for us to see what the balance is of the current contract's funds, basically our burger shop. So maybe we can say get funds, like so, and then this would be public, and it's only going to be a view function. Put our curly braces, and this needs to return something. So we also need to say this returns a uint256, and to have it return that, we can just basically say return address, and we're casting an address. And how do we get the address of this contract? We can use this keyword dot balance, okay, like so. Now we can basically, buy a burger, refund, and get funds. Obviously, these two functions don't have anything in yet, so let's go fill these up. Lastly, we can just also make the cost public so we can see everything we're doing once we start testing the smart contract. Now, for the most part, this buyBurger function is really not gonna do anything. So let's go ahead and set up an event so we actually have oversight which we can kick off in the buy burger function when someone actually goes ahead and buys a burger. So maybe we can say this is bought burger event. So you specify the event keyword, then a name, and then we define how the structure is going to look like. So let's actually go and put in an address. We're going to make this address indexed. Now, this is only necessary for if you have a front-end dApp or some kind of way that you want to look these up in the future, but I'm doing the best practices. So I'm going to make one variable or one parameter index. You can, I think you can make up to 3 indexed variables, but we only need one. Let's say this is the from parameter, so this will be an address, and maybe we even do a UN256, and let's give it the amount or the cost. So we're gonna pass 2 parameters in there. Okay, so when a burger is bought, we want to kick it off over here. So let's go and say, and this is how you use an event. You say emit, and then we say bought burger, and then you simply specify. So we want to say this is the message.sender, sender, and we also want to give the cost. Now, this is an interesting one, because do we put the cost of the burger, or do we put the cost of what someone actually bought the burger for? Now, I think we should make it just the normal cost. So I'm just going to put the cost of the burger, because maybe in the future our cost of our burgers change and we actually want to see how the price changed. So I'm just going to leave it as cost, and we'll see what happens. We'll see if this even kicks off right, if it worked. Okay, so that's for our burger function. Now let's go and have a look at our refund function. So fleshing out the refund function is easy. We just need to pass it an address, which we can call _2. This is just to say that we are going to refund this person. We can make use of the call function. So we first need to pass the to address to a payable, actual payable address. Then we can append the call, our curly brackets, the value, and then give it a value, which is going to be our cost up here. Because this is going to be a payable function, we just need to make this function payable as well. And then after the curly brackets, we put our normal brackets with quotation marks in there, and we end it off. Now this function returns 2 variables, which we can then catch. For now, I'm not going to catch them, so I'm just going to specify that we, maybe we'll catch the first one. So let's just say bool success. And we omit the second one by putting in this comma, and then we need to make use of the success. So maybe we can just return returns a boolean. So we're going to return a boolean from this function, like so. And that is it. So as you can see, this contract looks very cool, but currently it doesn't have any guard checks, and we are actually going to test this out right now and see what can go wrong with this code. So in order to test this out, you can go on Remix here on the left hand side to the deploy and run transactions. You need to make sure that you've got your burger shop selected, and then we can simply click on deploy. Now here you can see that it went through successfully, and if you click on this drop down arrow, this is where our contract functions are presented for us to interact with it. So to keep things simple, the red buttons are the payable functions, and the blue ones are public callable functions or variables. So these ones don't cost us any gas to use, and this is usually what dApps use to read data from a contract. So let's go and get the funds, and we can see there's 0 way in there. And the cost value for one burger is, remember, our 0.2 ether, but it's represented in way over there. Now, there is a significant big problem here. When you try and buy a burger, it's going to go through successfully, but yet we haven't sent any value into the contract because we're not checking for that. As well as if we refund someone, so if we paste in an address, this will also work. If we, however, use the contract as it's intended to be used, it will work. So for instance, if I am a new person and I want to go and buy a burger, so let me go and actually put in this amount of whey. So I'm going to try and copy this. I'm going to put this in as whey. You can see there's the whey amount. I'm going to buy a burger. And you can see that the get funds, it's now 0.2 ether. If I go ahead and do the same thing again, I can buy a burger by clicking on buy. It goes through successfully and our funds increase. But now I'm unhappy with my burger, so I'm going to say, well, I'm going to call these people up and get my funds back. So I paste in my address and I say, well, before I click that, just notice it's 99.5 over there. And I click refund and it's successful. Now it's 99.79. And I can maybe hit it again. Now it's 99.9 and just again. And all the funds are just, taken out. And these kind of functions don't take any precautions or actual logic to do these checks. And this is why guard checks are so important. Otherwise, anyone can do this. And also something that you've noticed is that any of these contracts, any of these accounts basically, can call all of these functions, which is a big no-no. So we need to go and put in some guard checks. So like I said, guard checks are there to make sure that the user input is validated and the behavior of the contract is validated to a certain degree, so that if something fails, it reverts and doesn't really change the state of the contract. So let's go ahead and look at how can we implement guard checks. Now, implementing guard checks, you get a few different options. You get require statements, asserts, and also reverts that you can use. I'll make a use of them in this contract so you can see the different cases where you might want to do a guard check to ensure some logic happens like it's intended to, and then you can decide where you want to go and put in your guard checks on your contracts. So one of the conventions that we can use is a require statement. Now let's take a look at the first thing that's really bothering everyone here, and that is the buying the burger. So buying a burger, people don't really have to pay for it in essence because it's just out there for free, right? Well, let's stop that logic and put in a require statement. How a require statement works is you type in the word require and put in the brackets. Now, what happens is it tells us that the logic in there needs to be true, otherwise it will fail. So for instance, we want to say that the message.value that comes into the contract when someone clicks on this function or calls this function needs to be greater or equal to the cost. Now, it's good to say greater or equal to the cost because let's say that it says equal to and there's for some reason one way amount off and your contract will fail. So usually checking for if the value is greater or equal to yes, that does open the door for someone to accidentally send more ether in the contract, but it's a safer option than to say if it's explicitly equal to. But anyway, you can decide what you want to use there. This is enough to block us from buying a burger without paying for it. Now, there's not really any feedback when these functions happen, so I actually want to get some feedback for if this fails. So what you can do as a second optional parameter is put in a string in the require statement. So the string we can put there is maybe something like did not pay, right? Or not enough. Let's think about a nice name or a nice string, right? I think not enough funds. Or we can say the burger costs more. I like that much better. So let's try the burger costs more, okay? And then let's run this function actually. Let's go and redeploy this contract and test this out and see how the logs can tell us what happens when someone tries and buys a burger and does not pay for it. So let's go and clear this out by clicking on this little dustbin, and then we can go ahead and deploy it again. Here's our contract at the bottom again, and this time I'm going to try and buy a burger. So I'm going to click on it and it says fail. You can clearly see that this transaction over here failed. If I can just pull this up a bit, you can see that it failed, and it even gives us a reason why it reverted. Here it is, the burger cost more. Now this is perfect for debugging first of all, and also informing people about what's happening in the smart contract. So sometimes it's a very good idea to put these extra strings as the optional parameter for the require statement, because it gives everyone an idea what went wrong in your smart contract. So let's go ahead and also try and put some money to buy this burger. So I'm going to click on the cost just so that I can copy this. Then I'm going to go ahead and paste it in there. I'm going to hit buy burger again, and here you can see it was successful. If we now open this in the debug log, what you can see though, remember we had this bought burger event. So scrolling a bit more down after expanding it, you can see that there's a section called logs, and in here you'll see that our bought burger event, which had a from and a cost argument, is depicted over here with the from, and the cost is displayed over here. Now this is a great way to save data on the history kind of logs of your smart contract, and dApps can then go ahead and use it to do some logic on checking the history, whatever it wants to check. But we are not done doing auth guards. This is just one type. Let's continue and see what other methods we can use to make this more secure. Well, let's go ahead and improve this require statement guard check over here. Now, we do get a concept in Solidity called modifiers. Modifiers can be added to any functions, and it's a great way to abstract logic that can be reused in other functions, like this require statement over here. Let's say we have multiple burgers and we want to check each one that the message is equal to that cost. Well, what we can do is create a modifier for that. So modifiers start off with the modifier keyword, and then we give it a name. So let's call this name maybe did or should pay. So our modifier is going to be should pay. That sounds like a fitting name. And then you can just specify your brackets and your curly braces. And then what a modifier does, it extends the function by giving it some logic and then executing the rest of the function's contents. How does it know how to execute everything in here of this function? Well, let's move this require statement. First cut it out and put it in your modifier, and then there it is. But now, after this check has ran, we need to execute the rest of this code. So you specify that by putting an underscore and a semicolon. By doing that, this modifier says it first needs to do these checks before it executes the code that this modifier is attached to. We haven't attached the modifier onto our function yet. So how you do that is after the public statement, you simply say this carries this modifier. So this logic should work exactly the same as it did. And we can test this by saving the contract, clearing it out, deploying it again, and then trying to buy a burger, and you can see that it still fails. The burger costs more. Now we can adapt this modifier to actually take in a parameter. So let's see how we can do that so that this becomes a much more reusable modifier for if we have burgers in the future that we also need to make sure that they should be paid for. We can take this concept even further. We only have this modifier that can work for one burger at a time. And what happens if the cost changes? Well, there's no way for us to reuse this modifier, and that's really why modifiers are there, to abstract the logic, and you should be able to use them on multiple functions. Let's say we had a new burger and we called it the deluxe burger, right? So let's just create a new function and let's say buy deluxe. All right. So that's the deluxe burger function. Keep in mind, this is not the best coding convention regarding reusability, because we can technically do this in one function, but I want to explain how we can reuse modifiers at this point. So let's say we also add an extra cost for the deluxe burger, and we're gonna call this one deluxe cost, and we have the normal cost. So let's just maybe specify that this is the normal cost. So now we need to just update everywhere where the normal cost or the cost was to normal cost, like so. And then let's go ahead and update our modifier to take in a parameter to specify what cost it should check against. That's very easy to do. You can simply create a UN256, and let's say this will take in a cost. It will check against that cost and only then will allow the user to buy the burger. We now have to pass a parameter to our modifier, and how we're going to do that is we're going to say, well, for the buy burger, we want them to pay us with the normal cost. And for the deluxe, we want them to use the deluxe cost, like so. If we now go ahead and test, this should all work as it was working before. Let's go ahead and test this out. Although we also need to update the normal cost over here for the emitter to the deluxe. And we need to remember to update the deluxe cost. Maybe we'll make it double. Now that we have this, we can go ahead and deploy our smart contract again and try and buy a burger. I'm going to click on burger, and it says the burgers cost more, right? And that's perfect. Now, if we go ahead and get the normal cost for the burger, copy this amount and put it as the weigh value, and we try and buy, it goes through successfully. But if we try and do this with the exact same value, the 0.2 ether, but we try and buy the deluxe burger, let's see what happens. We try and buy the burger, and it says the burger costs more. And that is indeed true, because the deluxe cost is this one. So if we try and put that in there and try and buy the deluxe, just make sure that you have the right value in there. When we buy the deluxe, we can see that it went through successfully. And that is a way where you can reuse a modifier by putting in a parameter and it handling the state accordingly. Doing the require statements, and you can have many more require statements in here, but handling those first before it executes any of the code that the function is attached to or that the modifier is attached to. So that's how we use modifiers. So we can now look at our refund function and make it a lot better. How we can do that is by adding a require statement to kind of check that we need to refund the correct value. Now we can't have this normal cost in here, because what if we need to refund a person who bought the deluxe burger? So what we can do is add an extra parameter, make it uend and call it cost. Then we can go ahead and put the cost in the value field over here. Before we actually go ahead and pay that person, we want to double check and make sure that the cost that we are sending in is either the normal or the deluxe cost. Keep in mind that this function can be called by anyone because we haven't discussed access control yet. But let's go ahead and assume that only the owner will be able to call this. You can say this needs to require something. You can say that the cost coming in needs to be either equal to the normal cost, or using an or conditional, the cost should be equal to the deluxe cost. Now that is enough for us to kind of block the owner from accidentally refunding some arbitrary weird number, because that number can either be this or that. Let's remember to put in our parameter to inform the debugger what's happening by maybe saying you are trying to refund the wrong amount if this fails. This check is brilliant, but it doesn't cover all the aspects of this refund function. What happens if there's really no value in the smart contract, like no one has bought but yet we are trying to refund? Let's go and put in a check for that. Right here below the refund check, so if we have already checked that the cost is, not some weird number, we can go ahead and create a new variable and call it the current balance. The current balance we can set to an address, which is this dot balance. So we're going to grab the current balance of this contract. So we can basically now just do a simple require statement again to check if the current balance is at least greater or equal to the cost being sent in. Now we can confidently check the cost because we know that the cost has already passed this require, meaning that we know that the cost, it needs to be at least less than the current balance that this contract holds for it to do a successful refund. But I don't want to stick with requirement statements the whole time, so I'm going to cut this logic out. Then I'm going to replace this with a if because I want to show you how the revert works. You can put this logic in an if statement and an else statement, like so. And we only want to proceed with this function if the current balance is greater or equal to the cost. Okay. If it's not, then we want to revert, and you can simply type revert like so. The revert will just start a revert session, and it will just say we cannot do any state changes, so revert everything in this function and stop the execution. We can then go ahead now and cut this out and put this in the if statement so that our logic works if this if statement actually passes, if we have enough balance in our contract. So like require, revert can also take in a string, and here we can just pass in the reason why we are reverting. So we can say not enough funds. Okay, and then once we have that set up, we can now just be sure that once this else conditional hits, we're going to revert, and all the state changes in the smart contract will be undone. Now this is very important, but why do we want to use revert instead of require? Well, require is for a more top level check, to check variables, to check parameters, to check state, actual local state as well. For instance, we can verify things up here. But revert is for more complex kind of scenarios. So usually we would use it in if statements or in very specific logical conditional statements where we need to revert quickly if we notice something is not right. So even though our if conditional looks good and we are returning this success, this function is not done yet. We really don't need to return a boolean. I just placed this in so that the function won't break. What we actually need to do is we need to kind of check that this went through successfully. So we're going to do a require in here, and we simply pass in the success. This time we're not really going to put in a reason if it fails, because I want to show you that you don't always have to put this string inside. But this is just good practice to make sure that it does do what it says it's going to do, like send the ether. Now the last mechanism that we have to our disposal when regarding guard checks is the assert. Now the assert is used for internal logic checks. It's used to absolutely fail if we're really sure that the contract should not behave in a certain way. Let's take an example where we want to use an assert in this refund function. If this is all said and done and it was successful, lastly, and absolutely very lastly over here, we can do an assert to check if everything was successfully executed. How would we do that? Now the assert mechanism is there in Solidity to test internal logic. It's to test that something should really not be out of place in your contract, maybe after execution, maybe during execution, whatever the case might be. But I'm going to use it here on the last line to assert that everything went well with the refund function. Now keep in mind, I can also use a require or a revert, and it will do the kind of the same thing. That's why I only use require and revert sometimes. That's basically all I need. But asserts are for those worst case scenario situations where if something goes wrong, you just want to stop execution and the whole execution will just stop. It will break. So let's go ahead and see how we can use it over here. On line 27, we can see that we have the current balance, which is saved in a variable current balance of the address. So let's say that for this function to be, to have executed successfully, we need to assert something. we're going to type the assert keyword, and the thing we want to assert, we want to make sure that the current balance now, which is the address, this dot balance, like so, is going to be equal to, if we were to take this current balance, which was over there, right, and we minus the cost. So that is a simple assertion. Now what this means is it needs to, after all this has happened, we need to have this assert and check that the current balance is equal to the minus the cost. All right. This means that it would have passed the revert. So this if statement was true, and it passed this all, and then it actually sent the money to a user, meaning that the current balance should be equal to the current balance that was over there, which we could probably give a variable name to say the balance before transfer, right? That would be a better name. So let's actually change it. So we're going to say this is the balance before transfer, and now that we have the balance before transfer, we can actually put it over there, okay? And we can also put it there. So this is a much better example where it says the balance before transfer is this. Then we check if the balance before transfer is at least greater or equal to the cost. Then we can go ahead and send it. Make sure that that passes, and if it does, we're going to assert lastly that the current balance is now indeed equal to that minus the cost. Because who knows, something might have happened in the smart contract, and in between this line and this line, something happened that maybe more money was sent, maybe it didn't work properly, and that's why we need this to be here. Now let's test this all out, and let's make sure that our refund function works properly. It's time so that we can test our smart contract. Now keep in mind there's no access control, so any address will be able to call any of these functions, but it's fine for now. We are just focusing on the actual guard checks. Now let's go ahead and go and deploy the smart contract. Let's click on the instance down here, and let's have a look at how we can test this out. Let's imagine I'm a new customer. I'm going to switch to an address. Then I want to buy the, let's see, the normal burger. So there's the normal burger's price, which is 0.2 Ethereum. I'm going to go ahead and paste it in the way so that I have my price set, and I'm going to buy, let me try and actually buy a deluxe burger with this. It's going to say you need more cost, right? The burger costs more, so that's perfectly fine. I'm going to go ahead and then do it again to just make sure that you paste it, because every time you scroll on the mouse wheel, it changes value. So just paste it in. Then I'm going to buy the normal burger. So I've bought one, and I can see that the funds coming into the contract is now indeed 0.2 Ethereum. So now let's say that I was not really happy with my burger, and I told the owner that I need a refund. So as the owner, now remember there's no access control, so I can do this from any account, but I'm just going to emulate that I'm now again on the owner's account. So I'm the owner, I need to refund a person. So I'm going to just for briefly copy this person's address. Then I'm going to paste it in the address, and I'm going to say that this person needs a refund, but let's say I take this amount, right? I put it in there and I add an extra 0. Now this, instead of 0.2 ETH, is now 2 Ethereum, which is definitely not right. I'm going to bankrupt myself if I now refund this much. But let me go ahead and transact and see what happens, because we have a guard check in place to prevent this. And there we go. The guard check kicks in and it says you are trying to refund the wrong amount. And thank goodness. Otherwise we would have given away our whole burger shop. But in this case where we can rectify it, we can take that out, that 10, and we can say transact. Now everything went through successfully. And that means that it means the right amount, it was either a normal burger or a deluxe burger. And obviously there are more checks you can do to make sure that you are refunding the right burger at this point in time. But the whole concept of this is just to show you the guard checks. So the logic of how it works would be still up to you to decide how you're going to do these checks. But I can indeed see that get funds now is 0 because we refunded everything, right? And now let's say I'm the owner and I don't look at what I'm doing, and I'm trying to refund another person, but it is actually one of these normal, these normal amounts, and I transact. It will say that there's not enough funds, meaning that I can't transfer more than the actual contract has, right? And that is a good check to have. It also means that the assert in our previous example worked because it didn't kick that previous transfer out. And this is a very good example. Keeping in mind that there's a lot more checks you can do with something like this refund function. For instance, you can basically check that the person indeed did buy a burger by maybe referencing a mapping that he was saved to, so that you just don't refund everyone who tells you you need a refund. So there's a lot more checks, but the stuff that I've shown you with the guard checks is enough for you to kind of implement that logic, making sure that your app flow and the logic and the parameters and how the functions execute in a correct manner. And that's the point of guard checks, to make sure that your input parameters coming from a person or an individual is correct, to make sure that the function executes in a correct manner that you want it to execute in, otherwise you revert, or at the end of the day to assert certain internal integrity of your variables. Okay, and that's about it. That is guard checks. So I hope you enjoyed this first pattern. Let's move on to the next one. The next behavioral pattern in our list, which is a state machine. Now, what are state machines? Because in essence, if we look at Remix, any smart contract is basically its own little state machine in itself. It has state, and it goes and implements a few functions that updates the state. Now, what the state machine pattern actually refers to is how do you update the state based on which stage you are at. I can show this in an example with our burger shop. Let's imagine for a second that there's only one person working at our burger shop. Highly unlikely, I know, but let's imagine that's the case. Let's say our smart contract can only take in one action at a time. For instance, we can only order, and then once we have ordered, the burger needs to be made, and then it can be delivered. But only after it's been delivered, then someone can order again, seeing that we only have one person working in the burger shop. Let's start this example off by creating our different stages that can take place. A good coding data type that we can use is an enum. An enum is basically a numbered, I would call it a list, but it's where you define words that represent actual integers. I'll explain in just a second. Let's call the enum keyword and then give it a name, and we can just call this stage. Okay? And now that we have a stage enum, we can say that this enum is going to have a few different stages. Now, what are the stages? Well, we have ready to order. Then we have to make the burger stage. And then we have the deliver. Those are my three stages. Now, we've got the ready to order. We've got the make the burger stage, and as well as deliver the burger. Okay? But maybe we can just take the keyword out. So ready to order, make burger, and deliver burger stage. Now, let's say that these functions, in order to make it a good state machine pattern or implement that, we can allow these functions only to be called on specific scenarios. The refund stage or the refund function can maybe be called anytime because it doesn't really fit in those stages. But seeing that there's only one person making their burgers, that person can only take the order in when we are ready to take the order. So basically these two functions can only be called once we're on ready to order stage. And then obviously we'll need to kind of make the burger, which the person making the burger would call, and it will transition to the next stage, deliver burger. And then the customer will have to engage with the contract again to pick up the burger for it to go to the next stage. Let's see how we can implement that logic. So now we've got our stages set up, and maybe it's a good idea to make this plural, stages. And the next thing we need to do is specify a parameter, like a variable, to save this stage, the current stage that this contract is in, because these are just the options, but now we have to define one. So let's give the keyword stages and make this public so we can see what stage it's currently on. And then let's give it an intuitive name like burger shop stage. All right. And then we can equal it to, maybe the first stage would be ready to order because we don't have any orders yet. So I'm going to equal this to stages dot ready to order, like so. Now in theory, this, and this represents basically 0, 1, and 2. So think of this stage as 0, 1, and 2. It's basically integers. And that's why you can increment with them and work all sorts of cool logic out with stages. It's just a better way. It looks better in code when you actually work with enums, because you get to assign a name to technically an integer. But nevertheless, we have our burger shop stage and it's ready to order. Now the next thing that we will need is a modifier. Yes, another modifier. This modifier will be checking at what stage this should be in order for us to execute the function. So we're going to need a modifier to add to our function, and let's start by defining it down here. So we're going to say this is our new modifier. Let's give it a name, is at stage. Sounds like a good name. It's going to take in our stages as a parameter. So we're going to say that the stages, we're just going to say it should be at a particular stage in time for us to execute everything on this underscore and the semicolon. Remember, everything here and here represents the code inside a function. But we still need our require statement to check our conditional. Now, what is our conditional? We basically want to see if this stage in the current point in time of the function execution is equal to the stage sent at is at stage modifier. Okay, so the is at stage modifier will be given a stage. For instance, it needs to be ready to order, and then that gets appended here on the function, and then it has to check that logic in order for it to execute successfully. Let's go and do that. So we can go ahead and now just check the burger shop stage and make sure that the burger shop stage is equal to the underscore stage that we've sent in here. Now let's go and append this is at stage to our functions down here. We have the buy burger and buy deluxe burger. And as I mentioned before, this is not the best practice to have two kind of functions that does the same type of logic. We can probably make it one. But let's leave it like that for our example. You can have more than one modifier on a function. So I'm also going to add the modifier is at stage and then pass it in the stage I want this to be only to be executed at. So I can say stages dot ready to order. So we want this to be there as well as there. Now this is interesting, right? Only when this stage is on ready to order will this be called and will the burger go through successfully. And that's what makes modifiers so reusable and so awesome. And this is the start of us implementing the state machine pattern. Now our pattern is not done yet. There's still a few more steps. So let's go and finish it up. So our state machine implementation is not done yet. Now, what we can do is we can basically create a function that will update our stage, because currently our stage is going to stay on ready to order forever. And that's not what we want. So let's go ahead and down here, let's go and create a new function. And I'm going to call this function update stage. This function is going to take in a stage. So I'm going to say this is stage. And then this is simply going to be a public function. Just to test it out, we can make it view. And what this function is going to do is basically update our stage of our burger shop. So if I go down, I can simply say that the burger shop is now going to be equal to our new stage. So we're going to use this, this basic implementation to keep on updating our stage. I see that the compiler has an error and it says function declared as view, so we can't call it view because it's changing state. But anyway, what I want to say is that the burger shop stage is going to be updated to whatever stage we give it. This is a useful function to have, and it can be an internal function, but for now I'm just going to make everything public so we can test it out if we need to on the outside. So let's go ahead and use this update state on the relevant places. I can already see that after buying my burger, I need to update the stage to make burger. So let's go ahead and update the burger. So what I want to do is, before I emit this event, I actually want to do that update. So I'm going to say update stage, and then I'm going to say stages.makeBurger. So this is going to update the stage to the make burger stage, and I also want to do the same for this function. You can already start seeing that we are duplicating code. Sometimes, especially when it comes to blockchain, duplicating code isn't a bad idea. It just should be done elegantly and also with a purpose behind it. The purpose behind these two functions being the same is really not a good example, and we'll probably get to refactor this at some point in this tutorial. But for now, just understand that we want to update the stage and then emit that someone has bought a burger. We have our state updated to the make burger state. Now our trusted employee needs to go ahead and make the burger, but we need to provide him with some kind of function that he as an employee can call to say I'm done, and the person can actually pick up the burger. Okay, so we can make a new function down here and say made burger. Okay, so the made burger function, all it's going to do, it's going to update the state or the stage to the stages.deliverBurger. Now, the reason why we want to do this is so that we can say, nice, we've made the burger, so update our stage. Usually in a real world example, you won't have a function that just does this. Maybe you will have, but it's very rare. You probably will have more logic going into a function like this. But for our use case, we're just going to make it simple. I'm going to refer to this variable as public as well. And then later on with access control, we'll see how we can have only the employee call this function. But made burger is now there. So this will update the stage to the deliver burger stage. So let's go ahead and create another function and call it pickup burger. The pickup burger function should be called by the client. So I'm going to make this public, and this again is going to update state. So I can just copy and paste that there. Let's just reformat, and then what happens after a burger has been picked up? Well, then we can put the stage back to ready to order. So ready to order stage, because now the cycle is complete. The employee is ready to make another burger and to take a new order. So let's go and see how can we finish this up before we can test this. So the last few things that we can update is actually giving these two functions that modifier that says they have to be at a certain stage. Okay, so the stage that we want this made burger to be called is only when the current stage of the contract is on making burger or make burger stage. So we can go ahead and say that the made burger function can only be called if the is stage at is make burger. So let's go and implement that and give this make burger stage. And then again for this function below it, we can say that the client or the individual ordering the burger can only pick it up when the deliver burger stage is ready. So we can say dot deliver burger stage. If it's at this stage, then the user can pick this up. Now let's just implement this is stage at and give it a string for when an error occurs. I'm just going to say this is going to be not at correct stage. Now we can most probably give it the stage, so we can probably give it the stage that it should have and output the stage, but we already know that we can access the stage with an external variable. So with this all done, the refund won't have this in place because you can call it on any stage. The employee will have to stop what he's doing and refund someone. But in the case that he is ready for an order, then these two functions should be able to be called. And then once it's busy being made, or the employee has made the burger, then he can call made burger. It should update the stage and a client should be able to pick up the burger. Now, keeping in mind, this implementation will not work in production at all because simply the logic is just not there to carry it in a full production implementation. This is purely just for educational purposes. Especially these functions won't really help, and you would need to properly brainstorm and work a scenario out and have proper function implementations. But as long as we can convey our two messages of the state machine and how it's implemented, that's all we want to do here. So let's go ahead and test out the contract. So this is the fun part of the tutorial series where we get to test it out. So let's go ahead and deploy this smart contract with our state machine and see how it's going to work. On the left hand side, make sure you're on a virtual machine, then select your contract, which is our burger shop, and hit deploy. Open the expanded contract over here, and here you can see we have got a lot more functions available for us. As you can see, we have the red buttons, which is the payable buttons. Then we have the orange ones, which still takes gas and performs state updates. And then we have the blue ones, which are merely there for reading of the contract. Now, the burger shop stage is important to me. I'm going to call it, and we'll see that it's on stage 0. What did I say about the stages? They start from 0, 1, 2. So we will be able to see this variable increment in an integer value, so it will become 1 when it's on make burger and 2 when it's ready and deliver burger, and then it will jump back to 0, hopefully, if it's successful. So let's just get the cost of the deluxe burger, because I'm going to pretend I'm a client. So I want to go and get a deluxe burger. I'm going to copy the cost of my deluxe burger, which is a 0.4 ETH burger. I'm going to put that value in there in weigh, and then I'm going to hit buy the deluxe burger. As you can see, this was now successful, and technically our state should have updated now to 1. So if I click on it, you can see that the stage is now at 1, and that's because this update stage was called when I bought the burger. What does this mean? Well, let's try and buy another burger. So imagine the employee went now and he's gone to make the burger. So a new client comes in there, and even though they go and put a value in there and buy a burger, it's just going to fail. And it's going to say not at correct stage. Now we know what stage it's on. It's still on stage 1. So the employee is busy making the burger. Employee is done. He's going to go ahead and say, well, I've made the burger, right? He cannot call pick up burger, or a client can't pick up a burger yet. basically, right? If we click on pick up burger, it's also going to say it's not at the correct stage because we're still at making the burger stage. But let's assume that the employee is fast and is done, and he's going to click on make made burger. So he clicks on made burger. We're going to check that our burger shop stage is now at stage 2, meaning that our stage is now currently at deliver burger. This means that the client is now ready to pick up the burger. Still, we cannot click now on buy burger. We also can't use the make burger. And if I click on it, you'll see it doesn't work. But the client first has to pick up the burger and take the responsibility off the employee so he's free to take more orders. So let me go and pick up my burger, and delicious, I've got it. It's successful. And we can see that the stage is now at 0 again. And this is basically what a state machine implementation pattern is. It's basically executing, making sure certain functions are executable on different stages, and how you set these stages or these different variables or conditions can be time-based, it can be conditional-based, it can be based on external contracts. You can go wild because it doesn't matter how you implement it, but this is the inner workings of a state machine in Solidity and on the blockchain, and basically on any coding language. If you are enjoying my series, please pause for a second and give it a thumbs up. Also subscribe if you haven't, if you want to learn a lot more of these coding concepts. If you are struggling, go and join our Discord or Telegram channels, and there's a lot of people that will help out. Lastly, leave me a comment in this description if you want to see something interesting, or you've noticed me doing something that you didn't quite get and you want to know the answer on. Let's jump on to our next pattern. The next pattern on our list is the Oracle pattern. The Oracle pattern is very handy for when you need to access data that's not stored on the blockchain. Let's say you needed access to some live chart or some value of the dollar, whatever it might be. Maybe you want to have a random generator sitting on an API, but the blockchain can simply not call that data directly like any normal Web 2 service. And the reason for that is because all the nodes that's hosting the blockchain will need to update that as well and do those calls, and there will be a tremendous amount of traffic. So how does the Oracle pattern solve the problem when we actually need to get access to external data from an API? Something to consider when talking about oracles is that the data that you actually want to consume outside the blockchain needs to come from a trustworthy source. Think about it. The blockchain is designed to contain data within itself. It has consensus algorithms to make sure that that data is solid and secure, and it's reliable, and that it acts in a specific way. So for you to introduce outside data and have variables depend on outside data creates a security risk. Just keep that in mind when working with oracles, and that you do use trusted sources. If you do that, then you should be fine. That being said, in today's example, I'm going to just do a small example of a separate contract, which we're going to set up our oracle, and then we're going to consume it in our burger shop. So when working with an oracle pattern, there are 3 main parts. The first part is the main contract on the blockchain who needs to use external data. So in our case, this will be the burger shop contract. The second part is the actual oracle contract, and yes, an oracle is a smart contract that lives on the blockchain too, that handles the request to the outside world. Then the third part is basically the outside world's data, the API. So the 3 main parts, how they communicate, is the main contract, the burger shop, quote unquote, interacts with the oracle. It sends a transaction saying that it needs that data. The oracle goes and sees if it has it, or it goes and reaches out and grabs that piece of data for the smart contract, and then it returns it with a callback that can be used in the main contract. Let's go and set this all up and you'll see what I mean. There are a lot of Oracle services out there that you can make use of, and all oracles cost some kind of money. But what you can do in this scenario is, let's imagine that the burger shop needs to reach out to the outside world to grab something. For a very basic example, we are going to query this API. It is the API that's just going to return to us JSON, and the simple JSON that this API returns to us each time we refresh is this object which has an activity field in it. Now I'm going to make this interesting, and let's say that our contract here, the burger shop, is going to give away lucky packets. And in our lucky packet, it tells you an activity to do instead of a toy. Way more active. So we're going to implement that, but to get our activities, we're going to reach out to an API to get that activity. This is not the best scenario because you can simply do it by just passing in some strings or an array and get the same effect. You usually would use this pattern for data such as charts, or really data that's difficult to get a hold of, or even random numbers. But nevertheless, let's implement this. To start off, we are going to make use of the Provable API. So the Provable API, here it is basically an API that we use and that oracles use to kind of make sure that it interacts with the outside world correctly, and that it can prove that it is the correct call coming back and forth from smart contracts. So we're going to use this library, and we have the first problem. We see that this library depends on Solidity version 0.5 and less than 0.6. That means to interact with a smart contract, because we're going to inherit from it, we kind of have to create ours in the same way, just to make it more convenient for the compiler to compile everything together. So let's go ahead and do that first. I'm going to say that we also want to use Solidity 0.5 and 6. Keep in mind, I'm going to undo this once we are done because I want to use the latest Solidity versions. When we do this, we should see some of our code down here, especially to do with the payable call function, not be valid anymore. Now what we can do is simply we can make this address in the parameter here payable, and then take out everything on the left hand side, remove this require statement, remove all of this, and then use the dot transfer, like so. We're going to transfer the cost. So once we have this ready and set in place, our smart contract should now be ready to be built again. So it was only that change that was outdated. Now we can go ahead and create our oracle in a different smart contract, so we keep the logic separate. We can do it basically inside of this contract, but I would much rather inherit from it. Let's now go ahead and create on our smart contracts folder a new file and call it the oracle.sol. Now that we have the oracle.sol, let's go and grab the license and the pragma line statements over there so we don't have to retype it. And then we're going to have to import a library. Now the import statement looks like this, and we need to import this library from GitHub. So let's copy the URL and paste it in there. And now we set up. Now we have to just create our oracle contract. Start off by typing out the contract structure. So we're going to type contract and oracle, and then we're going to say brackets. Now this oracle needs to inherit from some class in here, some contract, some library. So what we need to do is we will say is, and we want to find the is provable, or the using provable. So I'm just going to type out using provable, like so. And we can search for this using provable in this GitHub repository. And there you can see it, it's a contract. Now we're going to be using this because there's a bunch of functions in here that we need to call, actually only two that we are going to rely on. But let me show you how we complete the oracle. So the oracle pattern only relies really on two main functions. One function should go and get the data, or tell the oracle to go and get the data basically. And then the other is a callback that the Oracle sends back with the data, and then we decide how we want to use it. So let's start off by creating a string. The reason why I want to create a string because I need a placeholder to save our activity. So I'm going to actually copy that because that's going to be our string's name. I'm going to make it public and it's going to be the activity. Now we have our variable. The next function we'll need is the actual function that we can call to get our new activity from the API. So start off by typing out function and let's say get activity. Now that we have that, we can define this function. And this get activity is not going to really take in anything, but it is going to be public. So let's go and declare public. We can also make it payable because we have to send some ether to this function. Now in this library, we have this provable query. Where is it? Here it is. We have this provable query function that we need to call. Now this function is the actual function that would go out and go and get our API for us and refresh the data. And then it will come back in a callback function. But let's go and copy that and call it over here. Now this takes in two arguments or two parameters basically. And the arguments that we have to pass in is to specify the data source, which is going to be of URL. And then we need to specify the data that it's returning. Well, the data being returned here is JSON. And we can see that we need to specify that this is now JSON. So let's go ahead and type in JSON, all small letters, JSON, with brackets. And then inside the brackets, we're going to actually put our URL. So let's head back to our API and I'm going to copy this top part and I'm going to paste it inside this JSON bracket. And then after the bracket over there, I'm going to say .activity. And why do I say that? Because I want to get one of these fields, and this one that I am specifying is the activity field. I'm interested in getting the activity, so that's why I specified over there. Now, this is the first function that we need in order for this to call this library and go and get this data for us. But how do we retrieve it and how do we set our new public string variable to the new activity being retrieved? For that, we're going to need a callback function. Let's go ahead and specify our callback function down here. We're going to type in function and 2 underscores, and then we're going to write callback. Now, this callback function is going to be called, and it looks kind of similar if we just copy this and go into the library. It looks similar to the one over here. It's actually almost identical. So I'm going to go and copy this. So I'm going to go in here and replace this with that callback function. Now you see that it takes in 2 arguments, a my ID and the result. The result is this actual result from the querying the JSON. And the ID is to do with the ID of this transaction so that you can kind of verify it against each other to even make it more secure. But all I am interested in here is to basically check if this message.sender, right? We need to make sure that it is the contract that is sending this request. So we first need to go ahead and check that. So we can check that by entering a require statement and then specifying if this message.sender is equal to the provable address, which is a function sitting in our library as well. So we can say message.sender, like so, if it's equal to, and now in here, we should get a provable. So let me search for it. It should be the provable CB address. There we go. You can see that this returns an address back to us, and this is the callback address. So we basically checking if this is equal to the provable address, making sure that this Oracle is sending it back to the right contract address, if I can put it like that. Next, once this passes, we can basically set our activity now equal to our result. Once we've done that, we are basically ready. We don't have to use this below, and the compiler is going to complain because we're not using the myID. To simply omit that, I'm going to put it there and put semicolons at the end. So I'm not making use of this currently. But this is our whole implementation, and this should work. The only thing left for us to do is to go back to our burger shop and import this now. So basically what I can say is import and then specify my quotation marks. And I want to say that I want to import the oracle.sol like so. And then I want to inherit from it. So I want to say this is Oracle. And now that I've inherited from this contract, for those of you who've looked at the Solidity Beginners course, you'll know that the Oracle features or all the Oracle's contents are now accessible by the burger shop. So technically everything is now hooked up and we can test it out. In order to test this out, I have to go and be on a injected Web3 provider. So I'm just going to briefly switch over to the actual test network. So the Rinkeby test network. I see that I've got some test ether in there to deploy the smart contract. So it's enough for me to deploy and do my tests. Let me go ahead and deploy this. It says that the gas estimation below is going to fail, so let's cancel this and see why. I see that there's way entered in there, so I don't want that to be in there. I've got this set up to be the address that I want to deploy this from. Make sure that you're on the Rinkeby test network. I'm going to hit deploy again, and there we go. So now I'm going to say confirm, and once it's confirmed, I'll get my list of features, my methods that I can call to see if we can get back the activity from this API into our contract via the Oracle. There we go. So now you can see we have a lot more functions that we can call. Namely, we have this activity, which if we click on it, we can see it's an empty string. But now let's go ahead and let's go and set some ether. I'm going to send into this contract, I'm going to send 0.01 ether in way. So I'm going to convert it using this converter. I'm going to put it in there as the value. And I'm going to call the, let's see, where's my function? Get activity. I'm going to click on get activity. And now I can see that I'm passing in a value, and then I'm going to say confirm. This should go out and query the API, bringing back my JSON, and then assigning my new activity. Just a quick one before we go back to our test. If you want to find out how much an API call is going to cost, there is a provable price, which you can query, which will return to you the price. Let me just see, provable query, provable price. I think it's called provable price or cost. Let me just search for it quickly, because it works out kind of how much gas it's going to use. And there we go. Provable get price. That will actually be able to tell you kind of relatively how much you need to send to that call. But anyway, we've just sent 0.01 for the case to make it sure that it's going to be successful, right? Anyway, let's go now and click on our activity because it looks like it was completed. So now if we go and get our activity, we can see that our new activity is go swimming with a friend. Now that's a cool activity. So our API worked, and we actually pulled some data from the API into our smart contract through an Oracle. That is how simple it is to implement an Oracle. Like I said, be careful and mindful of which sources you use and that you can trust. You don't want to implement data that on a later stage won't be available and that can break your contract because you simply used an untrusted source. That being said, I'm going to clean up my contract again making this into the 0.8 contract that I wanted to use. So I'm going to backtrack my steps, make sure that I'm using the call again down here for my transfer, as well as making sure that I'm using my pragma up here. And now, because we worked in such a separated way, I can get rid of my oracle if I wanted to, but I'm not really going to do that. I just simply want to make use of the latest Solidity version. Now it's time to look at our next pattern, which is randomness, an interesting one. So why is randomness such a big subject and so difficult to get right? Well, first of all, and in all honesty, it's very hard to predict true randomness or get true randomness with code in general. And the reason is because there's some kind of predictable element that causes a random number to exist, right? But when it comes to the Ethereum blockchain, it's specifically hard because the Ethereum blockchain is made to be predictable. It's made to give you a certain outcomes every time you give it a input, it will give you the exact same output. That's how it works. And then on top of that, when you throw miners into the mix, miners are the individuals that needs to mine and validate blocks. Now, if a miner sees that there's some kind of randomness happening in a contract and there's enough incentive, like a reward that they can get from getting the right block number or what it is, they can simply withhold a block from being, mined, and then wait for that block to come along and then alter it, to their in their favor. But that being said, there is a way of achieving some kind of successful randomness on the blockchain by using a special method, which we're going to have a look at. I'm going to have a look at two ways, and one way I'm going to show you why it's not really secure to do it like that. And then I'm going to show you a better way which you can use. It takes a bit more implementation, but at least it's a safer option when dealing with random numbers. Let's jump over to our burger shop example, scroll to the bottom and create a new function. We're going to create a new function and call it getRandomNum. And then getRandomNum is going to simply return to us a UN256. So I'm going to make this view and also return UN256. And then inside here, we're going to make use of the kickback hash, which we're going to pass it in a bytes or string so that we can basically create a number, a numeric value, and put it through a modulus operator so that we can get a random number between 1 and 10. Let me show you how we can achieve this. Just remember to put your brackets after your function name. And then we're going to specify a new UN256 variable. And let's call this one randnum. This randnum is going to be equal to a casted UN256, just so we make sure it casted into the correct data type. We're going to specify we need to use the kickback 256 hash. So inside here, we're going to concatenate data types. So I'm going to use the ABI.encoded. I think it's encoded packet. I think it's encode packet, like so. All right, encode packet, and then inside here, we need to encode a few things. Now, we have got a few things available in the global scope, such as the block difficulty, the block timestamp, whatever we have, right? I'm going to use the block dot timestamp. So let's say block dot timestamp, like so. And I'm going to concatenate this with a parameter that I pass in here called the seed. Now I'm going to say this is going to be the seed, and then I'm going to concatenate this with the seed, and then after this all, I'm going to put a modulus of 10 plus 1, which would give me, so modulus 10 would give me a random number between 0 and 9. So if I want a number between 1 and 10, then I have to make it 10 plus 1. I can't make it 11, otherwise it's going to be between 0 and 10. So we're going to say modulus 10 plus 1, all right? And then we need to return this. So we can say return the random num, like so. Now, because this is public, we can go ahead and deploy this. So let's go to our JavaScript virtual machine, deploy the contract, and then go and find the get random num. Now here you can see, even if I don't pass anything in here, well, it's going to break. So let's pass at least 1 as our seed. This is going to concatenate the current block.timestamp with the seed, which is now currently 1. Then it's going to create the string of the bytes, which is going to pass into the kekak hash, which is going to hash it for us. And then it's going to give us a big number passed over here, which we're going to put a modulus symbol over there. So it's going to say this big number, modulus 10, will give us the remainder. But obviously it's going to be between 0 and 9, and then we plus 1. So we get a number between 1 and 10. I hope that makes sense. Okay, let's go and try it out. So get random num, I'm going to call this and I get 6. I'm going to call it again with 1, and you'll see that we get a different, how can I say, number, because the block.timestamp increments each time, as you can see. So every time I call this, the time increments, so it's every time a different random number. But what if I were to change this out and maybe give it a static value of 2,500 maybe, all right? And if I give it this value of 2,500, let's just maybe put this in strings. So I'm going to put that in string. And then this also tells me that this can be pure. So I'm going to make it a pure function. It doesn't require anything from the blockchain. So I'm going to do that, and then I'm going to redeploy this. So let's redeploy it, and let me show you what happens. So now if I put in 1 and I call it, I get 3. If I call it again, I get 3 again. And I get 3 to infinity because the variables stay the same. Now, you might say that, okay, but if I use block.timestamp plus a seed, that's quite hard to decode, right? So it's true random. Well, to a certain degree, it would work, but yes, a miner can still say, let me, withhold this thing from mining this block because I'm going to wait for a specific time, or whatever the case might be. There can be influence on this random value. So the better way of doing it is to actually do it in a staged way, where you kind of ask for a random number first and then do validation against it after, based on the previous block. So for us to fully understand the concept of implementing a better pattern to get random values and work with randomness, let's take a look at this example that this developer has set out. This is a great pseudo example which we can reflect on and look at, and I'll explain the code line by line. Keep in mind, this is not production ready code, it says over here, but this still conveys the concept pretty well. So to work a bit better with randomness, we want to eliminate the fact that the miner can actually prevent a block from being mined and withholding that block. So how do we do that? Well, we can set up 3 functions, and these 3 functions are just here as an example. The randomness doesn't have to be structured like this, but at least this conveys the pattern and why it is beneficial to do it in the staged manner, if I can place it like that, basically. So doing it in a staged manner, what we'll need is a few variables. So we're going to have a sealed seed, which is going to be the secret key that a trusted party is going to define. We have a seed set variable, which is initialized to false, bets closed, which is false, and then we have the stored block number, and then we also have a trusted party. Now, as you can see from looking at these variables, we can see that the bets closed is set to false, meaning that the bets over here, this function, can technically now be called. So everyone starts off by placing their bets. Let's say, for instance, I place a bet and I say a number out of 1 to 10, I'm going to choose 6. Okay? Now I've chosen my number and I've placed my bets, and a lot of other people do the same. When it comes to the time where it's now time for the trusted party to set the sealed seed, he goes ahead and does so. So once he does that, we have a new function you can see over here where the trusted party, this person whose address was defined by the owner, it can be the owner himself too, but that person has to give it a secret key, a seed phrase or whatever it might be. Now, these bytes get stored, right? But what happens first in this function? We check that if the seed is not set, this seed, if it's still false, and it also is going to require that the message.sender, the person calling this function, is the trusted party. Then on this line, we set the bets to closed. So as soon as this is called, there's no more bets. It's almost like saying, you know, if you're at a casino, no more bets, please. And that's what happens there. Then what happens is we save the sealed seed in this bytes variable at the top on this line, and then we store the block number. But now we don't store the current block number because that can be influenced on a later, well, on a stage, right, by a miner. So that's why we store a 1 block in the future. So we store the block number plus 1. Then we go ahead and we set the seed to true. So the seed was now set. Now all these variables updated, and this contract basically enters into the next phase. We already have all the bets that everyone has set. They cannot unset their bets because the trusted party called the stop and said, I'm going to set my sealed seed, plus I'm going to store the block number plus 1, which will help us later on in the stored block number. And now comes the interesting part. Once the sealed has been set, we are now allowed to call the reveal. Now this can be called by the public, so anyone can call this to reveal what the answer was and who won, right? But this requires a few things. It requires that we do have a seed set. It requires that the bet made, and this is now just pseudocode, sorry. So these functions might not all exist, but it kind of talks you through what should already have happened, right? It should require that the bets have already been made. And then it's going to require that the stored block number is less than the current block number. Meaning that, remember our stored block number over here, like that, is plus 1. So this function can only be called 2 blocks later, basically, or a block later, well, 2 blocks later. And once that happens, then it's fine. Then we're going to get a hash, and this hash is going to be based on the sender and the seed, right? So the sender plus the seed is going to be equal to the seed, the sealed seed over here. It's going to test if this is equal to the seed. Now, just by looking at this function, it looks to me like this is not a publicly callable function. It needs to be called by the trusted party because we're going to have to kind of verify that the hash of this trusted party and the sealed seed indeed is the seed, because here we pass it in. So the trusted party goes and sets the seed, and then the trusted party goes and reveals it with that exact same seed, right? And that's how we verify, by actually concatenating the trusted party's address with the seed. We're gonna see if it's equal to the seed. Now it would make sense if we, and I don't think it's mentioned here in this function, but it would make sense if at some point here we actually hash this same hash here in this function over here, because it means that we can get the hash and then compare them over here to make sure that we get a correct number. But anyway, here we see that the random number is now based off of this hash, and we put in the block hash and the store block number plus the seed. So this is going to be almost impossible for a miner to guess, and this ensures that the logic is quite solid and that you can now return the number that won to the person or give the person money, whatever the case might be. But here we go ahead and set the seed to false again, and betting closed is false, making the loop, making it loop basically. So now bets are open again. So the key takeaway here is to basically get a trusted party of some sort, combine it with a sealed seed and hash that with a block number +1. Then on a later stage, after the bets, right, after the bets have been taken, you do that. Then on a later stage, when it comes to reveal, you go ahead and hash the message.sender plus the seed, meaning that the same person has to actually go and put that seed phrase in there. And only when that matches, we know that we can now get the block number for that random winner. And that's basically how this extra kind of pattern of randomness works. I hope you understand that, and please let me know in the comments if there are people asking questions and you do understand it. Please assist people in the comments as well. Let's move on to the next pattern. The next pattern that we are looking at falls under the category security patterns, and it is the access restriction pattern. Now this is very self-explanatory, but how do we get and achieve a access level grant to a function basically? How do we give certain rights to certain people when executing functions in our smart contract? Let's take a look at our burger shop as an example and then add some access control to it. I also want to mention that if you want to dive deeper into access control, OpenZeppelin has a wonderful library called accesscontrol.sol, and in this access control you can read through the code, but it basically makes use of roles. You can give different roles, and then different roles can have access to different functions in your smart contract. We're going to look at a basic level access control pattern where we actually allow the owner of this contract to call certain calls, and then we can also make it time-based. A very simple and easy design pattern for access control that we can implement is by assigning an owner to the smart contract. Go and define an address data type, and let's make it public. Everything in this example is going to be public unless we explicitly have to make it private for us to test and show to you the values. I'm going to make this and call this is going to be the owner, and the owner is simply going to not be set yet. We have a construct called the Constructor function, so let's go and define the Constructor function. I'm going to call the Constructor function maybe after all my variables and enums and stages over here. So I'm going to type out constructor, and the constructor is going to take in an argument, or not really, it's not going to take in any arguments. All I'm going to do is basically set the owner over here equal to the message.sender, like so. This is a very basic implementation of the constructor function, and a constructor function only kicks off once in the deployment of a smart contract and never again. So the deployer of the smart contract will then be the owner, because here we are setting the owner, which is over there, to equal to the message.sender. Now we can, along with this, we can create a modifier for us to use. We want to create this as a modifier for us to use on a later stage as well throughout the application or the smart contract on different functions, basically, right? So let's type out and say, maybe we need a modifier to check if a person is indeed the owner before executing a function. So we're going to make the only owner modifier, and then this is not going to really take anything in, and all it's going to do, it is going to have a require statement that's going to say if the message.sender is equal to the owner, and that's all. And then we're going to execute it if it is. If it's not, it's going to stop execution. So now we can go ahead and apply this modifier to our refund function, because currently everyone can call it, but now only the owner can call this function. Let's go and test that out. Before we test this, it might be valuable for us to basically put in a reason if this fails. So we can just say not the owner, like so. This is not the owner, and that's why this is going to fail. We can also go ahead and implement different roles, such as the employee, and only the employee can maybe call the make burger function. We'll do that just now in a second. Select a new virtual machine here at the top so that we can get a new list of addresses. I'm going to select the top address, make sure your contract is on the burger shop, and then click on deploy. Now that we have this, I can see who the owner is, and it's indeed the top address. I am now going to try and refund someone after they have asked for a refund, but I'm going to be sneaky. I'm not going to be the owner, but I'm going to try and give someone a refund. Now, if I go and I call this refund method off the bat, it is going to fail because it needs the right parameters. So let's go and specify a few parameters that we need. We need an address. So if I go and expand this and put in the address, and then let's give it a cost amount. So let's grab this amount of a normal burger, and I'm going to say transact. You'll see that it fails, and the reason why it fails is not because there's no funds in the contract, because that's also the case, but the first thing that it fails on is because it's not the owner. And that's exactly what we want. This is the behavior that we want. So let's go and see how can we basically extend this to make it even better. Now, when it comes to access control, you can also do it on a time-based functionality. So let's go and assume that we have some sort of date that our burger shop is going to open. So before that, we can't call the make burger or really any of the other features. How can we do that? Well, let's specify a integer value and make it public. And we're going to call this the start date, right? The start date. And that's going to be equal to the block, because we have access to this global variable, the block.timestamp, like so. So this is going to be our start date, and we cannot call any functions if our burger joint hasn't opened yet, right? So we can go down here and let's just duplicate this modifier. I'm going to create a modifier to say has started or has opened, shop open, maybe shop opened. Anyway, we'll figure out what we want to call that. But basically all I want to check is if the current timestamp, right? So we can take this out and we can say that if the block.timestamp, right, is greater than the start date, and that's all we need. And then here we can say this is not open yet, like so. Now, this is going to work off the bat, right? Because the start date is going to be the exact same date as we deploy this contract. So immediately the shop's going to be opened. So what we can do is say, well, we need the block.timestamp plus, let's make it 7 days, like so. But we're not going to wait 7 days for this tutorial. So I'm literally going to make it maybe 1, or let's make it 30 seconds. I'm sure Solidity has seconds. There we go. So in 30 seconds after deploying this contract, our shop will be open. Let's go and apply our modifier, which is the shop opened modifier, to our functions. We know that we want our burger to have a modifier to say the shop should be open, this by deluxe burger as well. Our refund, maybe not so much because it's controlled by the owner, so maybe the shop doesn't have to be open. Maybe the owner, started off with a lot of cash and he wants to refund immediately. But the make burger should definitely have it, as well as the pickup burger as well. So these functions can only be called once the shop is open. Now keep in mind, it's also not really a good practice to extend on modifiers. So keep in mind, when this starts happening, you really need to start rethinking your logic. Maybe you need to reduce some of the modifiers or even compile some of them into one. But let's go ahead and continue with our test. I'm going to close the smart contract off, clear out my virtual machine so I can get a new list. I'm going to deploy my smart contract and then I'm going to open it. I've got 30 seconds to do this. So I'm going to get the normal cost of a burger and going to paste it in the weigh amount, and then I'm going to try and buy one. It's going to tell me that we are not open yet. Now I am going to have to wait for this burger joint or the burger shop to open. So let's pretend that we are waiting. I can also not call this because it's not on the correct stage. Now you can see that it started all the way from here, or should pay, and then also the stage. So it's just trying to see at which stage it was. I think the order goes from right to left, in all honesty. I'm not 100% sure, but we can probably test that out as well. Now, just that being said, it has been 30 seconds, I guess. So let me paste in the weigh amount again and buy the burger. It says pending. Now, the reason why it's saying pending and it's not going through is sometimes it doesn't tell you, but I'm pretty sure it went through. And let's see if we can actually call the make burger function now. So if we can call it, that's pending as well. So it means it worked. And then if we click on make burger again, it shouldn't work. It should say that it's not at the correct stage, which it does. So we can technically now pick up the burger. And then we're done. So that all worked. Now, like I said, sometimes it just doesn't return here. I'm not really sure why, but it stops doing that beautiful red and green after a while. Just refresh, remix, I guess. But the concept works, and we have a time-based access control as well as an owner-based access control. Now we can take this even further by creating employees or different roles, staff roles, and saying that different people assigned to this contract in that way can call certain functions. It's always a good idea to at least have one person always being able to call a smart contract function at any given time, especially if there's a possibility that it can be locked up forever, unless that's the intent of what you're trying to do, of course. But the reason why I'm saying that is because you can easily, with access control, if you're not careful, lock yourself out of your own features and your own smart contract, and it can be devastating if you cannot call the features that's needed to be called. Anyway, that is a little bit on access control. So the next thing that we are going to have a look at now is the checks effect and the interaction patterns. Now this pattern is so simple, but yet so powerful. Let me make a function to explain how it works. I'm going to create a variable here at the top, UN256. We're going to make it public, and we're just going to say this is the burger count. Let's equal the burger count to 100 burgers. Let's imagine our burger count is the amount of burgers we have to create in our shop. Now I'm going to basically use this by burger as an example. I don't want us to implement this and leave the implementation in here, but I'm just going to purely use it as an example to show you how to use it. Now let's go ahead and implement the checks effect and then the interaction. So let's imagine someone who buys a burger also gets a little bit of money back. So we're going to say that the message.sender also needs to get some money back, right? I'm going to use the old way of transferring ether. Just keep in mind this is the new way, just to keep it simple. So I'm going to say that the address, which we're going to pass as an address, okay, and we're going to say that this address would be the message.sender is going to be transferred a certain amount. So let's make this amount explicit. So let's just make it this much, like so. Now it's going to tell us that there's an error because we are using transfer, error send and transfer not available for address type payable. Okay, so we need to make this payable, obviously. So we're going to have a payable address, and we're going to send this much way to this address over here. But after basically this has been sent, we actually want to decrease the amount of burgers that we have. Now, how can we do that? Well, we can go ahead and we can say we're going to, after this, decrease the burger amount by just saying burger count minus minus. This is the same as saying burger count equals burger count minus 1, like so. So this is just a shorthand, minus minus. But here is the problem now. Let's say that we have got a person who buys a burger. Now the burger is going to update the state, and it's going to pay the person, and it's going to decrease the burger amount. But let's say that this function failed to pay back the person, and then they can redo this, but the burger amount never decreased because this is after the fact that this failed. Now obviously this will revert, but it still creates a re-entry problem for hackers to expose. So a better way of structuring this is first to do your checks. So let's also do another check. So let's just say a require statement. So we are going to say require, and let's just make it that the message.value is going to have to be equal to our cost. We're already checking for it here, but I'm just going to make it explicitly check it for it here again. Now, what we talk about checks, effects, and then interactions, the transfer or the call or anything outside of this contract is seen as an interaction. So a better way of structuring this is to first have your checks, which are the require statements, and the modifiers comply with this because it puts it at the top of the contract or the top of the function for that matter. But we first put our check, then we do the effects. So the effects are something like this burger count and even this emit. So we're going to do that, and then let's read our contract again. So firstly, it's going to say that we require that the message.value being sent to this contract is going to be the normal cost. Then we're going to update our stage. Then we're going to -1 from our burger count. Then we're going to omit this is what happened. And then we're going to transfer. The reason for this is because if it fails here, it means everything is going to be undone by the contract. It's going to say this is not valid, so it's not going to make the state changes, and it all will be fine. And that is basically the check effect and interaction pattern explained. Structure your code like this, and you will never really encounter re-entry problems. Like I said, I'm going to undo what I've done because I don't want to have these checks and transferring people money when they buy burgers. So we can get rid of this variable at the top as well. Let's look at our next pattern, which has to do with security patterns, and that is how to securely send ether, right? Secure ether transfers. For this example, I'll be going to this article Solidity by examples, looking at the ether transfer, send, and call. Now, you've seen me use in my example the transfer, and you also have seen me use this call method to transfer ether. And I mentioned that this is a better way of doing so, and I'll explain why now. Well, see, we get 3 three types of ways basically to send Ether. We get transfer, send, and call. But each one handles gas differently. Whereas transfer, takes in 2,300 gas and it throws an error if it's unsuccessful. Whereas send also takes in 2,300 gas, but it throws a boolean which you can then check against if it was successful or not. But then call, on the other hand, is pretty cool. This forwards all the gas to the necessary function that it needs to call to transfer Ether. Maybe it calls another contract that needs more gas to actually execute functions. And as well, it returns a boolean. So for me, using call is actually the better way of doing it. And in these examples, you can see that Solidity actually prefers you using the call method in the new Solidity versions. Let's look at transfer. On this transfer function, you can see that the comment even says that this function is no longer recommended for sending Ether. The reason for that is if you transfer using the transfer function and it fails, then your contract will simply stop execution and revert. The problem with this though is if it's an address, it's probably fine because it's going to transfer to that address. But what if gas just all of a sudden rises and it needs more gas to do something when you transfer Ether to an address? Because of the immutability of the blockchain, this can't be changed, and this function could potentially fail if this was sent to another contract that required more gas. So it's safe to really make all your transfers of Ether using the call method. So the address.call, and then you put in the value, and then you specify that it needs to basically transfer all the gas to this function call. This is necessary for, let's say you need more gas, you at least have the freedom to add more gas in your, or increase the gas limit in your function call so that it can forward the available gas to do the necessary steps. It's also cool because it does send back a boolean to tell you if it was sent successfully or not, that you can check against with a require statement, an assert, whatever you want to use. And that is simply how it works and why it's better to call the call function instead of the transfer. Send is in the middle of these two, where it mixes the 2,300 gas but still gives you a boolean. I would still say it's much better to call the call function. The next security pattern that we're going to take a look at is the pull over push pattern. This is particularly interesting, and I must say I fall short of using this pattern always. I like to create functions where a function will transfer Ethereum to someone's address because it feels so automated. But in some cases, it's not really the best scenario and the best pattern to use. It's much better to save that Ether inside a variable for that user, and then that user can go and claim their Ethereum. The reason for that is because you're shifting the risk of transferring the Ether to the user's pull method instead of the contract depending on pushing it to the user. Let me explain with a small coding example. Let's take a look how we can improve the burger shop contract by implementing the pull over push pattern. So what we can start off by doing is redefining how refunds happen in our contract. Let's start off by creating a mapping, and this is going to be a mapping of type address to UN256. This is basically going to be the mapping between who can claim refunds. So I'm going to call this refunds. Refunds like so, and maybe user refunds. That sounds better. Now I don't really have to make this public, but I am going to do that anyway. So because we might want to check it up when we test. But anyway, how can we use this mapping now to ensure that a user can only claim what's rightfully theirs, but also do it in a pull way instead of us pushing a refund towards them? So let's see how we can do that. Let's go down to the refunds method over here, and we can see that this is our refund method that the owner can call, and then we are automatically sending it with a transaction to that user. We want to eliminate this and actually have the user claim their refund. So what we can do is actually define a new function underneath the refund function, and let's call this function claim refund. The claim refund function is going to be payable because this function is going to be the one that pays the recipient, well, that pays the user who's claiming their refund. We can make this public and anyone can call this function. Now we're going to need a uint, and let's call this uint value. We're going to have to get the value from some specified, basically some specified value that the caller is allowed to withdraw. Now, as you remember, up here we had a mapping called user refunds, and we can simply claim it from the user refunds and specify the message.sender, like so. So now that we get the value from what this mapping holds, we can go ahead and send it. So we can basically cut this out and place it over here. Now I know this is messing up our structure that I've previously explained, but hopefully that's already in your head and you can rewind the video because we're going to reformat this refund function as well. Anyway, we now have to say that instead of just paying this to a to address because we don't have it, we need to kind of specify the message.sender, like so, message.sender, and then the cost is not going to be cost but value. And this is a simple way to kind of withdraw the money that is owed to a client. Now there's some extra checks that you can do, but this is basically how you convert a push, which this function was doing, into a pull. Now let's just refactor the refund function so we can actually test this out. So to change this up a little bit, we are just going to read through this function. We know that only the owner can call the refund. It's going to assign an address to and a cost to the person that it needs to refund. Now we need to do a simple check over here where we check for the cost, because obviously we check that the cost is either one of the normal or the deluxe, but we need to make sure that the balance, this address.balance, actually has that amount. So let's go and require that the address.balance is greater or equal to the cost. Now keep in mind, this is not a very solid check, because at this point, I'll show you now what's going to happen. We are going to assign that the user can refund the cost. So I'm just going to copy the user refund, and right underneath the require statement, we're going to say that the user refund to is going to be equal to the cost. That means that that user can now withdraw the cost, okay? So after that's done, what we need to do is we can basically take this out. This was just purely there, and we can even move this up to the check. Remember, there's the checks, effects, and interaction patterns, and we don't really need this. Perfect. Now let's go ahead and see what's going to happen when we assign this to the user's funds, because now we're saying this address will have this to withdraw. Remember, a user is going to claim this, but now we've got a problem because we still have this amount that this user can withdraw. So remember, our checks, effects, and interactions, we need to kind of set this to 0. So we need to make sure that after we have gotten the value of this user, we need to actually go ahead and do this and set this to 0. So that once we get the value, we make sure that we clear out that mapping and only then we go ahead and send. This is a perfect example actually of the checked effect and interaction, because if it fails here, this will be undone. But if we had this at the end of this function and we weren't checking for any state here for the require, if we weren't using this boolean at all, then this could cause a re-entry hack. So that's why you have to clear it out there. So now our claim funds are basically set up correctly. And if we look at the refund, there's still a little bit of a problem here. Because think about it like this. We are going to check that the balance is greater than the cost, and we're going to assign it. But when we do this again, it's still going to be, the balance is still going to be greater than the cost. So at some point, we'll probably need to put in a variable that tracks that the balance actually needs to be refunded first before we can check this current balance of the contract. So we probably need some kind of balance to deduct and add to, if that makes sense. Otherwise, we're going to lose track of how much is in the actual contract. But this is not the purpose of this explanation. The explanation is just to make sure that we move the responsibility of sending the ether to the user by claiming the refund. Let's see how this pans out and actually works. Let's go ahead and actually go and deploy the smart contract. So I'm going to clear this out. Then I'm going to make the top account my owner. So I'm going to deploy. Then I'm going to go to the second account over here, and let's just make sure our time variable, which is still set at 30 seconds, we'll need to wait for that before we can buy a burger. While we do that, let's go and grab the cost of a normal burger, like so. I'm going to grab the cost, and I also need to set the cost in there. Then I need to go and grab my address for later's use. So let me go and try and buy a burger. Hopefully the time of 30 seconds have passed. It's going to buy a burger and hopefully it's successful. Like I said, this is now problematic because I can't see if it's successful. Sometimes Remix just goes ahead and does this instead of showing the green. But anyway, we can try and see if we can give this person a refund because we sent some ether to it. So let's go to the owner and let's make sure that we copy the previous person's address. So let's go to the owner and let's say we need to refund this address, this amount. I'm going to paste it in there. I'm going to transact, and that went through successfully. Then I'm going to go back to the other address and just copy that address and find my mapping. There's my mapping. I'm going to paste the address and hit call. I can now see that I actually can go ahead and claim my money back. So now what I can do is I can simply hit the claim. So let's just read where it is. Claim refund. So check what happens to my account. We can see that I've got 99.79 ether in there. And if I now claim my refund, I can see that I've got 99.9. And if I now go and check how much I can claim, it is 0. And that is a basic example of actually doing the pull over the push pattern. So I hope you enjoyed that explanation and that you understand it clearly, that this is a better pattern to follow, obviously with the added notice that there's still some logic needed in the refund to track the true balance. Otherwise, we might give out more that a user can pull out. Let's now look at the last security pattern in our list, which is the emergency stop pattern. Now, this is that pattern that you should implement as a best practice, but the pattern that you never want to really use. And the reason why I say that is the emergency stop is exactly what it says. It's to stop the execution of crucial features in your contract and users from interacting with your contract. It does not always have to be users, but it can be contracts interacting with contracts, or functions interacting with functions as well. But basically what it comes down to is it's a safety check, a safety measure to stop execution if something goes wrong. And you also have the option to uncheck it if everything is fixed and your smart contract can continue as normal. So it's a very good practice to have this in your function or in your smart contract as a whole, just as an extra step of protection if something goes wrong. Let's go back to our burger shop and see how we can actually implement an emergency stop for if something goes wrong. So here at the top, and keep in mind there's a lot of proper libraries that you can use, such as Pausable from OpenZeppelin. But this comes down to a basic concept like this. Let's say we have a Boolean value and we're going to call it paused. Now this value we can also make public, and its initial declaration is going to be false. By the way, if you provide a data type and give it and do not declare it on startup, it will take the lowest value that it can be. So a Boolean should be false by default, and for instance a UN should be 0 and so on. Let's now go and implement a function that can switch these on and off. Let's scroll all the way to the bottom and make some space for our new pause function. So you can go ahead and type out the keyword function, and then let's just call this function pause. Now this pause function is only callable by the owner, so we're going to make it public, but we're going to add the only owner modifier that we had. Now you can see where reusability comes into play, especially with modifiers. So what is this pause function going to do? Well, basically all we need to do is set this paused Boolean true or false. So we can basically make use of the same function for this. We can say that we need to pass in a Boolean as an argument, and I'm going to call this the state, and then we're going to set the paused variable equal to the state. And that is it. We still need to now make sure that the contract, and if something goes wrong, that the execution of functions cannot continue. So we probably need another modifier for this, and at this point we have so many modifiers. Like I said, it's better to kind of abstract this logic in a different contract, have its modifier and inherit from it. But for this example, we'll just put the modifier right in here. Now I'm just going to copy one of these modifiers because I don't see us having to type it out again, seeing that we have done it so many times. This one we can say that not paused, let's call it not paused. And then what we're going to require is to say if the paused variable, you can basically say if it's not paused, but I'm going to explicitly say if this is equal true false. So this is explicitly typing this out. Now I can go ahead and I can go and put this on certain features. Let's go and put this on the buy burger functions. And the reason for that is these are actually the functions that we would like to pause so that there's no interaction from the community outside our burger shop. And there are other functions we can apply this to as well. But let me just do it for these two functions. Just gone ahead and refreshed my remix so that we can get proper execution and the nice green tick boxes if we do test our smart contract. I'm also going to go ahead and change this to 5 seconds instead of 30 so that we can test and start off our burger shop quicker. Let's go now and deploy our smart contract to test this out. I can now see that this was successful deploying the contract, and as the owner I'm going to try and buy a burger. So let me go and get how much a burger costs. This is the deluxe burger. It's about 0.4 ether. I'm going to paste it in there and I'm going to say buy a burger. And there we go, it's perfectly fine. So now the burger is being made by the employee. We can click on that and someone needs to pick up their burger. Well, let me go as the owner now and pause the contract. So I'm going to go there and say this pause the contract should be true. I can see that this is now, paused, and we can also verify it by looking at it there. So now technically no one should buy a burger even though someone has picked it up. So I'm going to pick up my burger, and now the cycle has complete. We should be still on state 1 now. So let's just see. If we look at the stages that we have in here, which is called stages, which is public, so we should have a visible eye on it. For the life of me, I cannot find the stages. Anyway, we are on we are on state 0, by the way, just to make sure that we are now going to attempt to buy a burger again when the contract is paused. So I'm going to do exactly the same thing, send in a value and try and buy a burger. And then you can see it fails and it reverts. Now we haven't specified a reason, but this reason is because the contract is paused. So if we want to unpause it again, we can go to our paused function and turn this to false. When we do that and we try and buy the burger now, it should succeed. There we go. Now that is how basically this emergency stop pattern works. It gets more into depth if you want to work with certain states, and based on certain states you can pause it, or time-based pauses, whatever the case might be. But it comes down to blocking execution that's crucial if something goes wrong. With our burger shop, I don't see anything going wrong from people buying burgers, apart from the fact that we still need to rework this refund, as well as, maybe rework these two functions. Let's just quickly look at a way how we can rework these two functions to be one. Refactoring these functions quickly, just to show you an example of how you can clean up code a bit better. Let's take a look at the buy burger function, and let's try and merge these two so we only have one function for the buying a burger. So now what we can do is, let's take in a UN256 and call it price. The person buying the burger is going to send in a price, and if it doesn't meet our expectations or it doesn't meet our price criteria, they can't buy any burger. So that's why we probably need to change the should pay modifier to not take in anything, and in the should pay modifier I'm going to explicitly say what it needs to be. So we're going to say if this value is greater than the cost, and this time I'm going to really say if it's equal to my normal cost. So if this is equal to the normal cost, or, so I can use the or operator and say, well, if the message.value is equal to the deluxe cost, like so. And this eliminates the fact that I need to actually send in any cost. So I can just have the should pay, and it means that I don't need this anymore. So I can just do this. Now I've got the price here that the person has paid, and maybe what I want to do is emit this, so burger bought. I can also say that we already have this, so we can say the price should be in there. And that way maybe the employee looks at the logs or the emission or whatever it is. We can also come up with a nice way of creating a ticket for someone to buy a burger. So basically what will happen is someone buys a burger, they put in a price, and if it meets our criteria of being either a deluxe cost or a normal cost burger, then they can buy the burger. And our program will then have to handle how it knows which burger was bought. But that's just a simple example of getting rid of these two functions and making it one. Now we can go ahead and just double check that we are not using it too much everywhere, or using these features everywhere. So I see we are using it in the refund, but this is fine. In the refund, this is also actually using the same modifier that we are trying to use, right? You're trying to refund the wrong amount. So maybe we can just say that this is not the correct stage, the burger costs more, and here I can basically change this saying not the correct amount. And now I can make this modifier should pay into being should be, or let's just change this to be correct amount, like so. And now I can use the correct amount over there, and I can also on my refund be using it here as well. So then I can get rid of that require statement. And this is how you start cleaning up your smart contracts by reusing modifiers, adapting them to actually have the proper logic that can be reused and so on. This is just a small example, but anyway, let's move on to our next pattern. We are now done with security patterns and going to take a look at upgradability patterns next. The first pattern that we are going to take a look at is the proxy delegate pattern. Now, proxy delegate seems quite difficult to understand, but in layman's terms, proxy delegate patterns just talks about giving the functionality or the responsibility of execution to another contract, but changing the actual storage values on the current contract that we are on. Now, instead of me coding along showing the delegate pattern, because we don't really have a use case in our burger shop for this, but let me take you through an article and explain the code and why we need sometimes to delegate calls and to make it very flexible for upgrading our smart contract. Keep in mind, using delegate calls are a bit dangerous, and if you don't use it correctly, you can mess up your code logic, especially on the contract that accepts that execution or accepts the state changes. Take a look at this example over here. We have two contracts, contract B and contract A. Now, contract A, let's assume this is our main contract. In contract A, you can see we have 3 state variables here at the top, as well as in contract B. It's important for whatever state you want to update in your contract A, that it also is represented in contract B, or whatever contract that's going to execute your logic. We then see that we have the set vars function, and this can be any function, but this doesn't really have any logic inside of it. Instead, what happens is it's delegating this function call or this function execution. You can see here by calling the contract dot delegate call, and then we passing in the signature, encoded signature. And what is a signature of a function? This is the signature part of a function, the name plus its arguments. Now you can see here by passing in the name and the arguments and passing in the argument that it's going to use, you passing it to the existing contract. Now this is just pseudocode, so it's not implementing this like it should, but basically you pass the contract address and then it goes and calls it. A good way of doing it is to actually save the contract address of your other smart contract in the contract that it's being used, which I'll explain in a example coming back here. But just keep in mind that it delegates. It's telling this smart contract that we want the execution to take place in contract B. And then when it starts updating variables, it's not going to change contract B's variables or state variables. It's going to update a contract A's state variables. Now, why is this important for us to kind of delegate functionality to another smart contract? Well, let's take a scenario. Let's say for our burger shop, we had a fund that we actually wanted to refund, or a certain amount that we wanted to refund to a user. But then we coded all the logic in our one smart contract like this. Seeing that the blockchain is immutable, it's going to be quite hard for us to update this functionality if we ever wanted to change. But let's say we used the delegate method or the delegate pattern. All we simply have to do is redeploy a new contract B and then point contract A to the new instance of B. And then we can go and update whatever logic this handles, and it will be linked up to the most recent contract and have new execution parameters or logic. So this example just shows that contract A can delegate calls to contract B, it executes and it updates contract A's variables. But how do we actually make it upgradable from a contract point of view? Well, we can go ahead and look at this example. In this example, let's imagine this was contract A that we've just seen in the previous example. We can see that we have a delegate, which is an address, which is the address of contract B after it has been deployed. Then we simply add a function to upgrade our delegate address. And that is enough to point this to a new address, a new functionality set, and that's how easy it is to upgrade variables or whatever functions you want to point to a different contract. This upgradability is very nice, but it adds extra complexity. So wherever you use it, it needs to be really thought of so you don't have to delegate all your functions to different smart contract calls. Now, it's also important to know when you use delegate, you kind of make your smart contract a bit more trustless, because now the person, let's say this was an NFT contract, needs to trust that you're not going to change the functionality because you are the owner. That sometimes is a trade-off between upgradability and trustability. But anyway, that being said, this is basically how it works. It's just a flexible way of delegating function calls to another smart contract. Now, you don't only have to do delegate calls like this. You can also just call functions normally on a smart contract. For instance, you can go ahead and have a caller and a receiver, and then all you have to do is basically call that function like here, that you can go and call on the receiver and so on. So you can basically interact with different smart contracts, and that's what I want to say in Solidity. And that's usually what you'll end up doing when you build bigger projects, and it's a very good pattern to follow. Let's look at the next Solidity pattern, which is still an upgradability pattern, and this is the eternal storage pattern. Taking a closer look at the eternal storage pattern, it's a very important pattern when you're working with upgradability on your smart contract and you are afraid that you might lose the actual stored data, such as user sets or NFT counts on addresses and so forth. We have to keep in mind that the Ethereum blockchain is expensive in gas when doing transactions, and it's simply not feasible to launch a new smart contract, look at the previous one and import all that data into the new one. That's why the eternal storage pattern is so important when you have a very upgradable smart contract and you want to keep that storage across all the other smart contracts even after it's been upgraded. This is a simple example, and you can imagine that the eternal storage pattern or the eternal storage contract is a separate contract on its own. So you might have your burger shop, for instance, and you might have a eternal storage for all your burgers that's ever been purchased. Now you can keep track of it by querying this contract and adding to it or subtracting to it, but basically this is only for handling the storage. So it's a separate smart contract that deals with all the different storage that you want to save. This allows you to simply go and delete or destroy the burger shop and deploy a new one and point those kind of addresses back to the eternal storage, meaning that you'll have the data saved. This is one example of how such a contract would look like if you implement it. You would usually have some kind of latest address that it can accept changes from, and those changes can only come from the set address that you give it. Otherwise, anyone can basically update the storage and play around with your data, which you don't want. You can also set up an owner so that you know that you can update your methods, such as the upgrade to the latest version of the contract. In the context of the burger shop, you would deploy the burger shop and then point the burger shop's address over here. You would also then go ahead and update an instance of this contract on your burger shop and point it back to this contract itself. That way the two are linked, and you can then set up your storage variables, which usually consist of a mapping which you can use a hash to an integer or a hash to an address. You can implement numerous data types like these. It's important to understand that usually each data type in a contract, like an eternal storage contract, has a getter and a setter method. What are getters and setters? Well, basically these are our storage variable mappings, and here you can see we have our getter methods and our setter methods. We also have delete methods if we want to delete a key. This works quite similar to actually having some sort of API where it's a RESTful API where we have the get, set, and also delete methods. But in this case, it's sitting on the blockchain and it is just purely there to handle the data entries and how we manipulate the data and store it. Now, what does a getter function do? All it takes in is a key, which is usually a hash, and then it returns a uint if we work with the integer values, and it looks through the mapping and it returns where that key was saved. When we set that key, we basically pass in a hash value, which would be the same one when we query the data back, but we set the hash key and we send a value. This time we see that it only comes from the last smart contract. It should be externally called, as well as then we can set up this key to the value that was presented to it. So it's these functions that sets, gets, and deletes data based on what you have set up here. So once you have all this data set in place, this contract will live on the blockchain forever. So it doesn't matter if you destroy, upgrade, or change or alter other smart contracts. As long as you can set the latest version pointing to your eternal storage, you will have a space where that storage is saved. Now, like I mentioned, with NFTs, it's most probably not a thing that people really do because everything just lives in the same NFT contract. But if you have more elaborate and complex structures of your dApp or a smart contract idea, whatever it might be, something like this would be a good implementation and a best practice to follow if you want that storage to persist. Let's now briefly skim over the economic patterns. These are patterns that will actually help you save gas when executing computations on the blockchain. Let's see what the three main things are to consider. Now, there's a lot more that you can do to save on gas, but these are things that most commonly can help you out. The first one is string equality comparison. Now, basically what it comes down to is if you take a look at this function down here, this is the hash compared with length checked. Now, the reason why we don't simply compare the two and then return from a hashed value, which is happening over here anyways, so simply this function could just exist out of this. But the reason why we first check the bytes.length is to save on gas cost. Because if we can simply check the length of the bytes of a string, it is much cheaper than first hashing the string and then comparing the two hashes. That's why when you implement this simple if statement before you return and do the whole hashing way, you can simply check if the bytes.length and this A represents a string and the B represents a string. Let's call it lips and hash, whatever the strings might be. But we convert them to a bytes and then we check the length of that bytes. If these are not equal to each other, then we can simply return false, meaning that we at least know that these won't be the same. And this is explicitly the case for when you have a string greater than 2 characters. Otherwise, it's always going to be true, and it's going to end up here in the hashing algorithm, right? So when your string is greater than the length, we can at least check the length. And if the length is not equal, then we simply return false because that would be the case. Lips and hash is not the same length. And well, let me just think about this. They are. So HashLips and lips are not the same length. So if we passed HashLips and lips, it would simply return false, meaning that these two are not able to be compared and they're not the same because it's simply a length check. But what happens if the two have the same length, such as hash and lips? Then it will come into the else statement and it will actually go and hash the first string and the second string and return to you the Boolean value if this is equal to that one. This just saves us on gas cost and computation that we do on the blockchain, and that's why it's a good pattern to implement. The next pattern that we can look are at tight variable packing. What does this mean? Well, basically it comes down to, if we look at our burger shop, when the compiler takes your code and turns it into bytecode, it has to read through it line by line and work out what it's going to do, where to save it, where to execute and output certain encoded data. So to make it easier for the compiler to do its job, tight variable packing is important. Let's take an example look at our burger shop over here. Theoretically, this should be fine, apart from one thing. Here you can see we have got two uint256, then an address, then another uint256. When it comes to tight variable packing, it's important to organize these. So let's cut this one out and let's put it right here above. It's important to organize these in little groups. So if you have a group of uint256 variables, group them together like this. If there were to be another address variable, group them together as well. Mappings, bools, and strings the same way. By doing this, by organizing your sets of data types into specific categories and groups, you make it easier for the compiler at least to compile at the compile time, and it will use less gas to actually put it on the blockchain. And that's basically, what it comes down to. And it's also a good pattern to follow. Not only that, your code just looks a little bit neater as well. Let's now take a look at the last economic pattern, which is the memory array building. It all comes down to a very simple concept. Whenever you change or update data on a smart contract, you pay gas for it. It needs to do a computation which costs gas on the virtual machine of Ethereum. But take a note, whenever we make a variable public on our contract, you'll see that we get a corresponding blue button. These calls are there and are gasless, well, at least gasless for the user. And by doing this, we can kind of aggregate some data using this getter function that Solidity creates for us at the back, and make use of it to construct an array of data and send it back to the user instead of querying data values one by one. Let me take a look at an example so you will understand a little bit better. Let's take a look at this example, the memory building contract. Let's say we have a struct which is called an item and it has a bunch of values inside of it. And we have an item array which is called public, meaning that we will automatically gain access to it via Solidity creating a getter function. We cannot get the entire array just by calling this if we want specific data to be in a data set. It's going to be pretty difficult doing it off-chain because we're going to have to query it, look at a condition and query again that data. Instead, let's aggregate our items into a new array in memory that we can return to a user. So what happens in here is we create a function get items by or IDs by owner, for instance, for an example, and then we go ahead and we create an array in memory. This is going to be seen as our result, and we're going to create a new array and we're going to set the length to the owner item count. Now this is all pseudo code, but technically you get the statically length of an array like that, and then we can start looping over it with a simple for loop. Once we start our loop, we can put any conditionals in there to populate that new array in memory, which then in turn gets returned to us, and we can make this a viewable function. And when something is viewable, it means it doesn't update or change the storage of the variables in the contract, making it very cheap in gas. And basically we can just simply call that and it's not going to cost us any gas. And that's how you can optimize your smart contract to maybe when you have a dApp or some sort of instance that interacts with your smart contract, to easily do so without paying a tremendous amount of gas to get data back to the front end basically. And that is it for our course on Solidity Smart Patterns. Now I urge you to go to the Provable Smart Patterns repo. You can go and check him out. It's very nice. Like I said, it was done in version 0.4, but following this video, I hope you got an understanding of how some of these concepts are implemented. Like I said, if you have any questions, please go ahead to our YouTube video series on Solidity Beginner Series, and also leave me a comment in the description. I really like to look at your comments and your suggestions. Also give it a thumbs up and a subscribe if you haven't. I will see you guys in the next video.